So you're having a party and mixing some cocktails, and then someone asks you to unmix them and recover the original ingredients. How are you going to pull that off? Or the DJ mixes a number of sounds together and then asks you to pull them back apart to recover the original sounds. Is that even possible? Surprisingly, we can do this by using linear algebra and geometry. Just like you recover the coordinates of an arrow by projecting it onto the basis vectors, we will project sound waves onto basis waves to recover their individual contributions to the mix. But in order to perform such a projection, we need two things. First, we have to figure out how to treat functions as vectors. Then, we need some kind of device to measure angles and distances between functions. After we set up those tools, we can get a pretty good grip on something as advanced as Fourier analysis. This is gonna be a video full of sounds and even some music. I hope you'll enjoy it. So far, we've seen two kinds of vectors: arrows and lists of numbers. Today we need another kind of vector, because we want to perform addition, scaling, inner products and other geometric operations on functions. To show you that functions follow the rules of a vector space, I want to start with a greatly simplified example first. We will begin by looking at a set of very specific and simple functions, polynomials of degree 2 or less. To turn these polynomials into a vector space, what exactly do we need? We really need only two things: addition and scaling. Can we add polynomials? Yes, just put the same powers of x together and add their coefficients. This gives you a new polynomial which will never have a higher degree because there's no operation that could create such a higher degree. Remember, vector spaces do not allow us to multiply the vectors. So even though a product of polynomials definitely exists, it doesn't exist within the vector space of polynomials. This is why the degree will never be more than 2. Can we scale a polynomial? Yes, just multiply all of its coefficients with the scalar. The result is another polynomial with a degree of at most 2. You can easily check the required properties for these operations yourself. Notice that both operations, scaling and addition, keep the different powers of x neatly separate. We already noticed in an earlier video that vector spaces always keep their dimensions apart, and that the operations of scaling and addition never mix them. Good, so we have our two operations, they behave as we want, and our set of polynomials is closed under those two operations. We have a vector space. Now, if you look at the algebraic shape of a polynomial expression, you'll see that it looks a lot like a linear combination. I mean, just look at it. We have a sum of terms, and each term is a scaled power of x. Do you agree that the powers of x clearly want to be the basis vectors here? When we treat them as three linearly independent basis vectors, every other vector can then be written as a linear combination of them. The space of polynomials of degree 2 is spanned by the three vectors 1, x, and x squared. Once we have a basis for our vector space, we can forget about the powers of x completely and treat our vectors as just lists of numbers. We focus on the coefficients rather than on the powers of x. This is what we also did for arrows. In a specific basis, n-dimensional geometric vectors are isomorphic to n-tuples, remember? Polynomials of a fixed degree n are also isomorphic to lists or tuples containing n+1 coordinates. See if you can figure out why it needs to be n+1. At this point, we can also easily define an inner product. As soon as you treat the coefficients of a polynomial as coordinates, you can just generalize everything we did in the previous video. So this inner product is still very close to the original dot product. Just as before, you just multiply the constant terms, the x coordinates, and the x squared coordinates. and then you add everything up. Please note that this is not the same as the multiplication of two polynomials. The result is a real number. Also note that there are many other ways we could define an inner product, and we will see a completely different one soon. Thanks to the inner product, we can now calculate the angle between two polynomials. These two are orthogonal, which you can easily see because they have no powers of x in common. They are similar to the two users who liked completely disjoint sets of movies. But again, these two polynomials are only orthogonal with respect to this specific inner product we've defined. Different inner products may give different results. Our set of polynomials is now no longer just a vector space, but an inner product space. Get ready, because we are about to crank up the abstraction level. We go straight from fixed degree polynomials to the set of all functions. Can you scale a function? Sure. You just multiply it with a number. This has the effect of stretching the function graph vertically. If your function happens to be a sine wave, you can think of the scale as the amplitude of the wave. Scaling it makes it louder or softer. Can you add two functions? Yeah. For every input x, just add the output values of the two functions. This results in a brand new function. It only works if the two input functions have the same domain, so we may have to limit ourselves to a specific interval. We'll do that later in this video. Either way, adding two functions is easy. It's useful to get some graphical intuition for this process. A great example is when you take the function f of x equals x, and then you add a second function to it that wiggles around the x-axis. Their sum turns out to wiggle around the 45-degree line, which is probably what you expected. Notice that f dominates the sum, because it's much larger than the tiny wiggle. This is why the result still basically looks like f if you squint your eyes. The same thing happens when we add a small wiggle to a big sine wave. The result still looks a lot like the big wave, it just has a little wiggle around it now. These examples should give you an intuition for what the sum of two functions can look like. With sine waves, you can even hear what it sounds like. The sum of two sounds contains both sounds at once. Your ears can still easily pick them apart. Okay, so functions can be scaled and they can be added. That's all we need. We conclude that functions do indeed form a vector space. The next thing we want to do is find a good basis. Remember that the polynomials of degree 2 had a really simple basis, the 0th, 1st, and 2nd powers of x. This time, when we try something similar, we get an infinite number of powers of x. We can write many functions as a power series, which is basically a linear combination, but with infinitely many terms. So it seems that we have infinitely many basis functions, which would also imply that our space of functions is infinite dimensional. Is that really true? Is it even allowed? The answer is yes, it's allowed, but it creates a few technical challenges. I don't want to get into those challenges here, because it would distract from the main story. In the applications we're going to look at, everything works out fine. So we are allowed to write down these infinite linear combinations. That means that you should think of the coefficients of a power series as the coordinates of our function in an infinite dimensional linear function space. It now becomes very easy to scale and add such power series. Just scale each coefficient by the same factor, or add the coefficients pairwise. Because the powers of x never mix, the coefficients always stay separate, just like the apples and oranges in the previous video. You may never have thought about power series as linear combinations before. It's a really useful perspective, because it allows us to do linear algebra on functions. If we can somehow find a good inner product, that will allow us to do geometry on functions as well. We could try to take inspiration from the dot product again, but this fails. For polynomials, we only have a finite number of coefficients, so we can multiply them pairwise and add them up. But for functions in general, the power series has an infinite number of coefficients. We can't just add those up, because the resulting sum could diverge. We need a different approach. We will start from the ordinary product of the two functions. For each input value x, both functions spit out a number. We multiply those numbers pairwise. If you do this for all values of x, you get a brand new function, the product of the two input functions. This is cute, but it's not what we want. We want the inner product to produce a single real number, not a complete function. So here's what we will do next. We will calculate the area underneath this new function. This area is given by the integral of the function over some interval that we have to explicitly choose. The area between our chosen lower and upper bound gives us a real number, exactly what we wanted. And that's why the inner product of two functions is typically defined to be the integral of their product over some interval. I know this formula is a bit more scary than the one for the dot product. There are a few differences, but there are also similarities. Instead of pairwise multiplication of coefficients, we have pairwise multiplication of function values. And instead of a discrete sum of a finite list of numbers, we have a continuous sum over an interval. That's exactly what integrals do. They sum an infinite number of tiny pieces together. Note that the integration interval is an important part of this definition. Different choices of interval will give us different inner products with different properties. The best choice of interval often presents itself automatically. It typically follows from the context, as we will see soon. In spite of its more intimidating form, this expression still just produces a single real number as required. Just like many other inner products, we use a notation with parentheses. The two inputs are the functions f and g, not just individual function values. We are operating on entire functions at once. When you plug the same function into both inputs, you get a square under the integral. This always gives a positive result, so that's another one of our requirements that we can check off. Thanks to its positive value, we can then take the square root to obtain the norm of a function. You could think of this as the abstract length of the function if you want, although it's hard to imagine how you would visualize that. Basically, we're just measuring the area underneath the graph of the square of our function. The only way this area could ever be 0 is our function was literally f of x equals 0. It's reasonable to say that two functions are orthogonal when their inner product is 0. Again, this is difficult to visualize, but it will come in very handy in a few minutes. In the previous video, we defined lengths and angles via the inner product instead of directly. We could have just applied Pythagoras and trigonometry directly on the arrows, but that would have given us the measurements for arrows only. It would have left us totally clueless about how to generalize these measurements to functions and other more exotic kinds of vectors. By taking the more abstract detour, we now have to generalize only one thing, the inner product, and the rest comes out for free. So far, we have expressed our functions as power series, or in other words, as linear combinations in the specific basis 1, x, x squared, and so on. We're now going to change to a different basis. Sure, the powers of x are easy to understand, but they're actually not a very good set of basis functions. The main reason is that they are not orthogonal to each other. Pick an interval such as 0 to 1, calculate the result of the inner product integral over that interval, and you will see that the result isn't equal to 0. So the powers of x are not an orthogonal basis. Instead, let's switch to a different set of basis functions. We will replace the powers of x with sine and cosine waves. We still have a series, a linear combination, but it has sines and cosines as its basis functions this time. Instead of a power series, this is called a Fourier series. Our main goal will be to find the coefficients for this series. I'll try to take it slow and explain everything step by step. We start from a simple sine and cosine function. These are periodic. They repeat every 2 pi radians. So it's very natural to limit ourselves to the interval from 0 to 2 pi. See, I told you that a logical choice for the integration interval would present itself. It just follows very naturally from the periodicity of the waves. A single sine wave sounds like this. This one has a frequency of 261 vibrations per second, or hertz. When we double the frequency, the sound goes up by exactly 1 octave. Our ears are very sensitive to the exact proportions of these frequencies, so that a doubling of the frequency sounds pleasant. Note that the double frequency still fits nicely into our chosen interval. All of our waves will have a frequency that's an integer multiple of the main frequency. That's important for the pleasant quality of the sound, but also for our mathematical treatment. All of the waves we will consider will fit exactly a whole number of times in the interval from 0 to 2 pi. Apart from the frequency, you can also change the amplitude of the wave. To create more interesting sounds, we add multiple sine waves together, each with its own amplitude. Here's the earlier example again, where we start from a big sine wave, and then we add a much smaller wiggle to it. The wiggle has a smaller amplitude, so you barely hear it. It gives the sound an edge, makes it slightly sharper. This is what the linear combination of our two basis waves sounds like. Note that the result, once again, fits nicely into the main interval. So, for our set of basis functions, we will pick infinitely many sine and cosine functions. We will create sounds by producing linear combinations of these basis waves, each with its own coefficient. Each coefficient scales the corresponding wave before it goes into the mix. The bigger the amplitude, the louder that wave's contribution to the total sound. The value of n can go from 0 to infinity, and it tells us how many times the wave goes up and down within our interval. So it's related to the frequency of the wave. The higher the frequency, the higher the sound. For n equal to 0, the sine becomes 0 and can be ignored. And the cosine becomes 1, which gives us a constant term in our linear combination. In practice, we don't want such a constant term, because it gives a permanent average push on your boombox, which would not be healthy for it. So we often force its coefficient to be 0. Okay, I hope you see how this works. Linear combinations mix individual waves together to create layered sounds. What we want to do now is do the opposite. If somebody gives us a layered sound, we want to decompose it into its components. We are given a sound signal with a period of 2 pi, and we want to find the simple sine and cosine waves from which it was constructed. In other words, we somehow need to recover the coefficients in the linear combination, starting from the sum. That's what Fourier analysis is all about. It's a technique for unmixing a signal. This is not just a cool theoretical mathematical puzzle. Fourier analysis has many real-world applications. For example, if we can recover the big wave and the small wiggle from this input signal, we can then remove the small wiggle from the signal altogether. This could be useful for removing high-frequency noise from a bad recording, or to create cool sound effects and filters, or to separate the heartbeat of a mother from the smaller and faster heartbeat of her unborn baby on a sonogram. Those are all real-life applications of Fourier analysis, and hence of linear algebra. Okay, so the goal is to pull an input signal apart into simple waves. How would you go about this? Think about it for a moment. Viewing the input signal as a vector, we want to recover its coordinates in our basis. Which techniques from this video and earlier ones would you use? Well, I actually already gave the answer away at the start of the video. If we were talking about an arrow, we would recover its coordinates by projecting it onto each of the basis vectors. We derived the formula for projections in the previous video. The coordinate is given by this fraction of two dot products. In an orthonormal basis, the dot product of a basis vector with itself is 1, so the denominator goes away. All that's left is the dot product between the given arrow and the basis vector. So in an orthonormal basis, we just need a single dot product. We already saw in the previous video that this is one of the many things the dot product can do. It extracts coordinates. But we're not talking about arrows. We're talking about functions. You already know that the inner product for functions is given by this integral. We multiply the two input functions with each other and then integrate over the interval we're interested in, from 0 to 2 pi. At the front, we also put an extra factor that normalizes the product. Its purpose will become clear in a moment. When we fill this inner product integral into the projection formula, it becomes this monster of a fraction, with integrals in the numerator and in the denominator. Can we please somehow simplify this? Luckily, we can, but only because our basis functions turn out to be orthonormal. That makes the denominator disappear like before. This is one of the many reasons why orthonormal basis functions are so cool. They make the formulas and calculations much easier. Now, I'm not going to actually prove that the sine and cosine functions are orthonormal. This video is already getting quite long. You can find the proof in this link in the description. Just to give you a quick intuition for how the proof goes, if you plug two different basis functions into the inner product integral, you can apply many of the trig identities that you may have had to memorize in high school. This simplifies the integral considerably. It also helps that the boundaries of the interval are 0 and 2 pi, where many of the expressions involved will turn out to be 0, so that many of the terms will cancel. And that's how, for two different basis functions, the integral manages to always be 0. You can see this by looking at the function graphs, where the product of two different basis waves has an equal amount of real estate above and below the x-axis. The integral adds this all up, treating the stuff below the x-axis as negative. Everything cancels out very precisely, so the result is indeed 0. This proves the orthogonality part. But it gets even better. When we use the same basis function twice, the integral turns out to have a value of pi. This happens for all frequencies, so for all basis functions. On the graph, you can see that all of the real estate is above the x-axis this time, because the expression under the integral is a square. The integral is positive, and it evaluates to pi. And now you see why we placed a factor of 1 over pi at the front. It normalizes each function so that its length or norm becomes 1. This makes our basis not just orthogonal, but orthonormal. And that causes the denominator in the projection formula to disappear. Its value is 1, so we can ignore it. And this is the answer. This is the formula for calculating the AN coefficients. It's cool to realize how similar this is to the way we found the coordinates of an arrow. We projected the arrow onto each of the basis vectors, and that's how we obtained its coordinates. Here we do exactly the same thing. We project our input signal f onto each of the basis functions, the sines and the cosines. The result of the projection is the coordinate of f along that axis, along the direction of that basis function. You can do this for all basis waves in turn, to obtain all the coordinates of our function. All we have to do then is use these coordinates as the coefficients in the linear combination. So this set of formulas gives us the complete Fourier decomposition of a periodic signal. These are the formulas you will find in the textbooks, give or take a few details. But forget about those precise details. You now know exactly what this formula means. Geometrically, it's just a projection of the input signal onto an orthonormal basis of waves. Now that we have this result, let's play around with it for a while. Let's build a simple sound filter, just because we can. In calculus, you write the exponential function as a Taylor series, which is a linear combination of powers of x. You can approximate the exponential by cutting off this power series after a sufficient number of terms. The terms keep getting smaller and smaller, so you can ignore them to get a really close value. Likewise, you write a periodic input signal as a Fourier series, which is a linear combination of waves with different frequencies. And just as with the Taylor series, you can create a good approximation of the input signal by cutting off the series after a sufficiently large value of n. This turns the series into a finite dimensional vector, without losing too much of its quality. But what you can also do is cut the series off at a value of n that is deliberately too low. This means that you will remove all the higher frequencies from the signal, which makes it sound dull and grounded. Then you can slowly increase the cutoff frequency to make the sound open up again. This is a popular effect in music. The key thing here is that higher frequencies sound sharper. So as you open up the filter, the sound becomes sharper again. This is known as a low-pass filter because it allows the low frequencies to pass, while cutting the higher ones out of the linear combination. The cool thing is that such a filter literally does nothing more than cutting the higher terms out of a series. It's mathematically extremely simple. The coefficients of a Fourier series are often plotted on a graph like this one. This line means that the cosine with frequency 330 Hz occurs with a coefficient of 100 in the series, which means that it has an amplitude or loudness of 100 in the mixed signal. This collection of frequency lines is called the spectrum of the sound. It allows you to see the difference between low bass sounds and high sharp ones. This basic sine wave all by itself has the simplest possible spectrum. Its linear combination consists of only one term, the sine wave itself. So there is only one non-zero coefficient in the series and only one single line on the spectrum. Here is a triangle wave. You can see that its spectrum also has a single large peak, followed by a set of coefficients that are much less loud. That's because, visually, the triangle wave looks a lot like a pure sine wave. It takes only a few small wiggles on top of the sine wave to produce a fairly close approximation of the triangle. You can even hear that a triangle sounds very similar to a sine wave. Now look at this block wave. Its frequency spectrum has many more wiggles at much higher frequencies. That makes it sound a lot sharper than the sine or the triangle. Visually, you can see that the block wave has to make a very tall vertical jump, and it can only do this with very fast sine waves, in other words, with very high frequencies. So just by looking at the shape of this wave, you can already predict that it's going to sound a lot sharper than the triangle. When we put a low-pass filter on the block wave, it removes the higher frequencies and the sharpness of the sound goes away. As I close the filter almost completely, only the lowest frequency sine wave remains. You can now see why it has the highest amplitude in the mix. It already covers quite a lot of the block. Everything else is just smaller wiggles on top. Now that we understand Fourier analysis as a kind of projection, there are also two other perspectives from which we can look at it. Both offer great intuitive insight into what Fourier analysis does. First, remember that an inner product not only performs projections, it also measures the correlation between its two inputs. So this inner product here not only tells us the coordinates of our function along each basis wave, it also tells us how much our function correlates with each of the sine and cosine waves. 3 Blue on Brown has a great video about Fourier analysis from the perspective of correlation. Say I give you this input signal and I want you to find a sine wave in there. You just slide your test wave over the input signal until they match up. Right there. This is where the input signal and our test wave look the most similar. And there's that word similar again. As soon as the similarity or correlation between your test wave and the input is high, you can conclude that you've found a match. My simple explanation here can never do justice to this beautiful process. The 3 Blue on Brown video has, as always, sublime animations to make you feel the details in more depth. The main point is that this uses correlation to explain Fourier analysis instead of projection. Later we will see yet another perspective from which these techniques can be understood. It's called the least squares method, and I can only briefly sketch it here because it involves even more calculus than all the integrals I've already been throwing at you. Let's imagine that we've done some experiment to measure something. Maybe we've recorded a whale sound underwater, or we have used a camera to measure the position of a vibrating guitar string. We get a scattered set of measure points. Because this is the real world rather than a clean mathematical model, there's a lot of noise in this data. The points are a bit all over the place, but you can still see the vague shape of a wave in there. We want to recover this wave from the noisy data. So we will try to match a sine wave to the data as best as we can. The least squares technique goes like this. We first calculate the error, the difference between our guess and each of the data points. We square these errors and then we add them all up to get the total error. Then, as we slide our test wave across the data points, we find the position where we minimize the total error. When you hear the word minimize, that might trigger memories of derivatives and tangent lines. A function reaches its minimum precisely where its tangent line becomes horizontal, so we will have to calculate the derivative of the total error. This is basically the slope of its tangent line. We want to know where this slope becomes 0. I will spare you the details of the calculation. After a few steps of calculus and algebra, it leads to a system of equations with a matrix full of integral formulas. Lucky for us, the sine and cosine waves that we're trying to match satisfy all kinds of trig identities. This makes it super easy to solve the system of equations. And look at that! The solution is exactly the projection formula we found earlier. And because the sine and cosine waves are orthonormal, all the denominators are equal to 1, and we get our previous result back. Just marvel at this for a moment. Using calculus to minimize the error, we uncovered exactly the same answer as using linear algebra and projections. You could even say that what we have here is a roundabout proof that shows that a projection always yields the smallest possible distance, the closest possible approximation, the minimal error. It's crazy how the inner product brings all of these techniques together. I mean, we started from a pure minimization problem, and it found the correct formula for the inner product. All of the calculus and algebra that goes on behind the scenes automatically forces the solution into the form we already expected. Wow, that was a lot of fun. I've really enjoyed experimenting with sounds and low-pass filters. The music for this video was made by someone I personally know. You can find more of his great compositions on his SoundCloud. The link is in the description. I would really appreciate it if you paid him a visit and liked some of his music. Of course, you can also do the same for this video. I know we covered some pretty advanced stuff today, so don't be afraid to ask questions in the comments. We will do our best to help clarify everything. Next time, we will begin our exploration of linear transformations and matrices. We will look for the eigenvalues to predict the long-term survival of animal species in an ecosystem. And we will find patterns in big piles of data. You can already watch the rest of the series on Patreon. It would make a huge difference for us if you supported us financially. Thanks for your kind contributions. It really helps a lot.